In lesson 14.4, you will solve trigonometric equations. First, we're going to find the general solution of 4 times the cosine x plus 1 equals negative 1. So what we want to do in this trigonometric equation is get our function alone. So we want to get cosine x alone. So we'll start by moving that 1 to the other side of the equal sign, getting the product for cosine x alone on the left, and we have a total of negative 2 on the right hand side. And now we'll divide both sides by 4 to get our function alone. So we get cosine x is equal to negative 1/2. Okay, now looking for x, looking for our solution to this equation, we need to know in what quadrants the cosine is negative. So if I look at that right triangle in all 4 quadrants and apply the definition of the trig functions, I know that in the first quadrant, sine, cosine, and tangent are all going to be positive. Those ratios will all be positive. But in the second quadrant, where the adjacent side is negative, when I apply the definition of sine, which is opposite over hypotenuse, that ratio will be positive. But cosine and tangent will both be negative, because adjacent over hypotenuse is negative and opposite over adjacent is also negative. In the third quadrant, where both legs are negative and the hypotenuse is positive, the sine, which is opposite over hypotenuse, is going to be negative. The cosine, which is adjacent over hypotenuse, is also going to be negative. But the tangent, which is opposite over adjacent, negative over negative, is going to be a positive ratio. And we have the fourth quadrant left. So applying the definition of sine to that triangle, we get opposite over hypotenuse, which is negative. Cosine adjacent over hypotenuse is going to be positive, and tangent opposite over adjacent will be negative. So we want to know what quadrants we're going to find a solution for x in for the cosine x equals negative 1/2. Cosine is negative in the second quadrant and the third quadrant. So that's where we're going to name terminal sides. And if I apply the definition of cosine to this triangle in the second quadrant, adjacent over hypotenuse, I have negative 1/2. And if I finish that special triangle, 1 to the square root of 3 is the ratio of its sides. And I know that that reference angle that we're looking for is a 60-degree angle. So now I need to name that terminal side in the second quadrant, and I need to name that terminal side in the third quadrant to solve for x. So x is going to equal 180 degrees. Take away that reference angle of 60 degrees, so we're talking about a 120-degree angle, or x could equal 180 degrees plus that reference angle, plus 60 degrees, so 240 degrees. Now we want to leave our solutions in radians, so I'm going to change 120 degrees to radians, and that's going to be equal to, since pi over 3 is equal to 60 degrees, we're talking about 2/3 pi radians in the second quadrant. And in the third quadrant, we're talking about 3/3 and 1/3 more, so 4/3 pi to name that terminal side in the third quadrant. And because we want general solutions, up in the directions it asks for a general solution, we're going to have to add on 2 pi n so that we can circle this coordinate plane any number of times and come back to that terminal side. N is an integer, so we can let n equal 0, 1, 2, 3, and so on, and we can travel that coordinate plane any number of times in the positive direction and get back to those terminal sides. We're naming coterminal angles, an infinite number of them. Okay, in the second example, we want to find the general solution of sine x times tangent squared x equals sine x. So we're solving for x again, and we would want to get 0 on one side by subtracting sine x from both sides, get all of our terms in this equation on the same side of the equal sign, and 0 on the right. Okay, and then I have two terms on the left-hand side. I have sine x in both terms, so I'm going to factor out that common factor of sine x from these two terms, and that's going to leave tangent squared x minus 1 in parentheses. And now that I have this equation factored, I can use the zero product property. I can set those factors equal to 0, sine x equals 0, or tangent squared x minus 1 equals 0. So in this first equation, our function is alone, sine x is alone, but in the second equation, we're going to have to add 1 to both sides to get tangent squared x alone, and then take the square root of both sides to get just tangent x. So tangent x, taking the square root of both sides, is going to equal two solutions plus or minus the square root of 1, which is 1. Okay, now let's find solutions for x in our first equation. Sine x equals 0. So we have to go to the coordinate plane and decide where the sine could be 0. Well, because sine is opposite over hypotenuse, to get 0, we'd have to have the ratio 1, 1, 0. So we'd be talking about x equaling 0 degrees or 0 radians. And we'd also get 0 for sine when we rotate 180 degrees or pi radians, because opposite over hypotenuse is also going to be 0 over 1 for that ratio. And to name 0 and pi, and to name that solution in general, we could just add on pi n. And that way we rotate every 180 degrees or pi radians, and we're at a terminal side, at a solution. Okay, that's part of our solution, and now let's look at tangent x equals plus or minus 1. We're asking where on the coordinate plane is the tangent going to be both positive and negative. Well, that's going to be in all 4 quadrants. So we're looking for terminal sides in all 4 quadrants. So let's apply the definition of tangent to the first quadrant, and our ratio is 1 over 1. So opposite over adjacent, 1 over 1, the legs are both 1. And when we finish that triangle, that special triangle, 1, 1, the square root of 2 is the ratio that we need. So we can see that our reference angle this time is equal to 45 degrees. Okay, and to name that terminal side in the first quadrant in radians, that would 45 degrees would be pi over 4. Okay, and we're naming in general, so if I just add on pi n again, I'd circle the coordinate plane every 180 degrees or pi radians. So I'd not only name the terminal side in the first quadrant, but I'd also name the terminal side in the third quadrant. So I'm continuing to rotate as many times as I want around this coordinate plane, and I'm always naming the terminal side in the first quadrant and the third quadrant with that notation. Okay, but we still have the second quadrant and the fourth quadrant terminal sides to name. So if we went halfway, that would be 4/4 pi, and we need to back up a fourth. So that terminal side in the third quadrant is named with 3/4 pi radians. And again, if I add on pi n, I'm rotating 180 degrees or pi radians, and I'm naming the terminal side in the fourth quadrant as well. So again, we'll rotate a half turn over and over again to name the general solution for this equation. Okay, in our last example, we're going to solve 1 plus the tangent x equals the square root of 2 secant x in the interval x is between 0 and 2 pi. So we don't have to name general solutions here. We can just name solutions once around the coordinate plane. And to solve this equation, I look at tangent and I look at secant. The only way I can relate them would be or the best way I could relate them would be to use the Pythagorean identities. So I'd want those functions squared. So I'm going to begin solving this equation by squaring both sides of this equation. So on the left-hand side, I have a binomial squared, and a binomial squared is going to be a trinomial. So when I multiply that binomial to itself, I should get 1 plus 2 tangent x plus tangent squared x. And on the right-hand side, when I square the square root of 2, I'm just getting 2, and then I'm going to square secant x and get secant squared x. Okay, now I can use the Pythagorean identity, and I can replace secant squared x with 1 plus the tangent squared x. And then I have one function in this equation. But I also have parentheses, so I'm going to have to distribute and get rid of parentheses in my next step. So 2 times 1 is 2, and 2 times tangent squared x is 2 tangent squared x. Okay, now I'm going to want to get 0 on one side of this equation and see if I can factor and use the zero product property again. We want to treat this equation like a polynomial equation. So I'm going to get 0 on the left-hand side here by subtracting these 3 terms from both sides. So I'm going to have 2 tangent squared x minus 1 tangent squared x. That's 1 tangent squared x. And then I'm going to have a negative 2 tangent x for a middle term. And when I subtract 1 from both sides, I'm going to have 2 minus 1, or 1. So I have a trinomial to factor on the right-hand side, and that trinomial should factor into a binomial times a binomial. So if I factor that first term, tangent squared x, into tangent x times tangent x, those factors go here first in my binomials, and the only factors of 1, the constant term, are 1 times 1. If I make them both negative, then my middle term is negative 1 tangent x plus negative 1 tangent x. That's negative 2 tangent x. So my factoring checks, and what I have is a binomial times itself. So what we factored was a perfect square trinomial. And when I use the zero product property, since those binomials are the same, I only have to set one of them equal to 0 to get my solution. So tangent x is equal to 1, or 1 over 1. And now I have to go to the coordinate plane to look for my triangles. Where is the tangent positive? That's going to be in the first quadrant and the third quadrant. So I'm looking to name terminal sides in the first quadrant and in the third quadrant. So I'm going to label that triangle in the first quadrant opposite over adjacent, and I'm going to recognize that the special ratio is 1, 1, the square root of 2, and theta prime, my reference angle that I need, is a 45-degree angle again. Okay, so x in our equation is going to equal pi over 4, and that names the terminal side in the first quadrant, and another solution then will be the terminal side in the third quadrant, which is 4/4 plus 1 more fourth. So a total of 5/4 pi in the third quadrant. Include with your notes of this video guided practice problems 1, 5, and 7 on pages 933 and 934 of your textbook.